So we've looked at situations where an object is moving along a line and maybe interacts with another object. And in those cases, linear momentum has been conserved. And then if we have situations where a system can pivot about a point and there's a collision, then we can say angular momentum is conserved. But what if we have a situation where both things are possible, where the object moves through space and then it collides with another object, causing rotational motion, and the whole system moves forward? Well, let's take a look first of all at a slightly simpler situation, and then we'll look at that sort of a craziness. So this graphic shows a particle striking an extended object, which is what we're going to be looking at here. A particle that moves and either sticks to or bounces off an extended object. This situation is simpler though. It's the particle, the blue particle, is coming right at the center of mass of the orange extended object, and so there is no rotation that results. The red X that's in the picture represents the center of mass of the system. And so everything is completely lined up. The center of mass of all the parts lies along a line, and so we stick with just linear momentum in this case. Okay, so just linear momentum. The R and the V of that blue block point parallel to each other, and so R cross V would be 0. There would be no angular momentum. Ignore the shapes, just focus on the masses. But if we have a situation like this, where that blue particle is not heading towards the center of the orange, you can see a couple of things. First of all, notice that this red center of mass point is no longer in the center of the picture. It's no longer in the center of the orange object. It's shifted downwards because the blue object is below. So one of the things is that you have to know where the center of mass of the system is, not sort of before the collision, but after the collision. Where is that point about which the system is going to rotate? And then once you find that point, then you can find the angular momentum of the particle about that point. And you can find I for the extended object and for the particle about that center of mass point. And then you can use our ideas of angular momentum being conserved. But the center of mass point actually does continue forward at a consistent rate, just like it does when you have a simple linear collision. And so if you only focus on the center of mass position for each of the objects, then you can actually still use linear momentum, and that will be conserved as well. So there's actually two ways of analyzing the system. One is to look at the center of mass point with linear momentum, and one is to look at the rotation around that center of mass point and look at angular momentum. So let's just summarize this. If you are trying to find the speed of the center of mass or the linear speed, something to do with the linear speed of a part of the system or the combined system, then you can still continue to use linear momentum ideas. Kind of forget about the fact that everything has a shape and just look at how it moves across the x-axis. But if you are interested in the rotational motion of the system or of a part of the system, you got to first locate that center of mass point so that you know what the axis point is. It's not going to be given to you because the system isn't nailed into the wall. And in that case, you can write the angular momentum values around that point, calculate I around that point, and use our conservation of angular momentum.